Hey, so in this lesson, we're going to be talking about function operations and composition of functions. So our goal eventually is to be able to find the inverse of functions. So we need to be able to, when we do that, do the composition of functions. And we also need to be able to look at other functions where we do have to add, subtract, multiply, and divide. So first of all, just to make sure you understand, when we're literally talking about operations, we're talking about those basic functions you started learning in elementary school. So when we're writing the addition of two functions, it's written like this is one type of notation. Sometimes it's also written like this, f of x plus g of x. And it literally means take each function, add them together, combine like terms, etc. Subtraction can be written f of x minus g of x, and they are both pronounced the same exact way. And again, literally, it just means take the first function, which is written there, subtract everything in the second function. Now, this, I want to make a note of, that little symbol there, that little teeny closed dot middle circle, means multiplication. You learned that hopefully by the time you were in middle school. I don't want you to confuse it with something we're going to be doing later on called composition of functions. Okay, so if we're multiplying two functions, we also can write it like this. And when we're dividing two functions, we can also multiply it like this. Okay, an important note about the domain of the function. When we're looking at the domain of a new function, it's the intersection. Okay, remember the symbol for intersection is this, and it's everything that the two sets have in common. So for example, if I had a set of numbers 1, 2, 3, and 4, and I'm going to call it set A. And then I have a set B, which is the numbers 1 and 4. So if I take A and I intersect it with B, then I want what they have in common. So what do I see is the same in both? I see that they each have a 1 and then each have a 4. So the intersection would be 1 and 4. Second thing to make sure you know about when you're dealing with functions is that whenever you're dividing, the domain is going to be further restricted because the denominator can never ever be 0. So for example, if we end up with a function that looks like this, what number can't I divide by? Well, I can't divide by 0. So if x plus 2 was 0, that can only occur if x is negative 2. So I know that x cannot be negative 2 in the domain, which means my domain would be every number but negative 2. So I would write that as negative infinity to negative 2 in union with negative 2 to positive infinity. Okay, now let's go ahead and we're going to do a little bit of a practice with operations with functions. So here I have defined for me my two functions, f of x and g of x. And over here on the right, it has add them, subtract them, multiply them, and divide them. Okay, so first let's go ahead and look at adding. So, and what this literally means, remember, is take f of x and add g of x. So I'm going to go ahead and take x squared plus x, because that's f of x. I'm going to add 3x minus 1, because that's g of x. And now I'm going to combine like terms. So there's no like term for x squared. There is a like term for x and 3 of x. And there is no like term for the constant. So this is f plus g of x. Okay, now let's go ahead and take those same two functions, but this time we're going to subtract them. So again, these are my two functions, and we're going to do subtraction. Okay, so again, we're using those same functions, and literally, again, what this means is take f of x and subtract g of x. So my f of x is x squared minus x. The only thing I need to be careful about with subtraction is to remember I'm subtracting everything. So I have to distribute that minus sign. So this is x squared minus x minus 3x plus 1, and then I combine like terms again. So I have x squared minus 4x plus 1 is the sum of f, is the difference of f minus g of x. Okay, next we have multiplication and division. And I am going to focus when we do these two on the domain as well. Okay, so multiplying, remember, this symbol means f of x times g of x. So f of x is x squared plus x, and g of x is 3x minus 1. So it's a binomial times a binomial, so I'm going to go ahead and distribute twice. So that gives me 3x cubed minus x squared plus 3x squared, and then negative 1 times x, negative 1x. So now I go ahead and I combine my like terms, and I'm going to go ahead and finish up right here. And I get f times g of x is equal to 3x cubed plus 2x squared minus 1. So when I'm looking at what the domain was, I originally started with a quadratic, which had all real numbers, times a linear function, which had all real numbers. And what I'm ending up with is a cubic function, which still has all real numbers. There's no value of x that I can't use. So the domain is still all real numbers. Now let's go ahead and look at division, because the domain is going to give us a little bit of a different thing. So this says to divide f of x divided by g of x. So there's my division line. In the numerator, I'm going to put f of x, x squared plus x. The denominator, I'm going to put 3x minus 1. I'm going to check to see if there's anything I can divide out. So in the numerator, I'm going to factor out x, because they both have a common factor of x. It leaves me x times x plus 1. In the denominator, there's nothing I can factor out. So in order to simplify this like a fraction, this has to appear exactly in one of the two factors in the numerator. And it doesn't. Even though I see that all three factors do have an x in it, you can't just divide by x. So this is as simple as I can make it. Now the issue with the domain, and by the way, this would be our answer to what is f over g of x. I can't divide by 0. So what's the value for x that's going to make this denominator equal to 0? Well, first I add 1 to both sides. Then I divide by 3. And so what I'm saying is that x can't be 1/3. So the domain can be any other value except that one. So let's write the domain. So the domain would be all real numbers. So an integral notation, starting at negative infinity. But when we get to 1/3, we have to skip it. So we put in union with 1/3 to infinity. This means all real numbers with the exception of 1/3. So this is example number 2. And just to note, we're doing these operations with functions. The only thing I have to be careful about is anything that's going to restrict the domain. So here, my function is x squared plus 9. That's a parabola. And the domain is all real number. But on this one, the function is the square root of x. And remember, we cannot take the square root of a real number that's negative and have an output that's a real number. So that means that my values of x that I can use all have to be values of x that would give me a positive number or 0. So in this case, my domain is x has to be greater than or equal to 0, because anything less than 0 would give me the square root of a negative. And so remember, that restriction is going to carry through on some of our operations. So what I want you to do is just go ahead and pause the video and go ahead and evaluate. Okay, so for f plus g of x, you should have simply just gone x squared plus 9 plus the square root of x. And the domain is that you can't have a value for x that's less than 0. So in interval notation, you would write 0 with a bracket, comma, infinity. F minus g of x, it's x squared plus 9 minus the square root of x. And again, the domain would be any number that goes from 0, starting at 0 to infinity. For multiplication, you should have gotten x squared plus 9 times the square root of x. There's other ways you could write this. If you distribute the square root of x, you would get square root of x times x squared plus 9 square root of x. Then, what is the restriction on the domain? It's the same. The domain has to be a number that's 0 or greater. And the last one, it's really simple. It's just x squared plus 9 over the square root of x. And then our restriction for our domain this time, square root of x, if we set it equal to 0 and we square both sides, we get x is 0. So if x is exactly 0, we get a 0 in the denominator. So that has to be a further restriction. So in addition to us not being able to use any negative numbers, we also can't use 0. So instead of putting a bracket, when I describe my domain, I have to put a parentheses to say, don't include the 0. Okay, next we're going to go ahead and we're going to talk about composition of functions. So a composition of functions, again, just to feature what we're going to be using it as, we're going to be using this to determine if two functions are inverses. First, we're going to know what it is. It's considered to be an operation of functions, and it's a way to combine them. So I always think of it something like your body functions, and it's a composition of it. So if, like, for example, digestion starts with your mouth. Your mouth does something, the enzymes in your saliva activate things in the food which help you to digest it. And your stomach does something else. But your stomach is depending on stuff happening already in your mouth, which is why you always feel a little funny when you just swallow things straight away without chewing. Ha ha. Anyway, that's a composition of functions, and you know how it ends. So when we're writing the composition of functions, it's defined as f of g of x, which means every place in f of x, which is that first one given, you're going to replace it with g of x, or every place in f of x that you see in x, you're going to replace it with the entire function g of x. Now, composition of functions is not always what we call commutative. So if you see something that's written like g of f of x, this means in every place in g of x that there's an x, you're going to replace it with f of x. Okay, important note about the domain of the composition of the functions, when it's in this order, okay, then g of x has to be in the domain of fx, is how we define it. Here's a little mapping to kind of illustrate that. So let's suppose we have a function f of x which equals x plus 2. And we have a function that says g of x is 3 times x. And I want to go ahead and I want to do f of g of x. So let's say I put in a 2. And the first thing I'm going to do is I'm going to g it. So I get 2 plus 2 gives me 4. That's the result of g of 2. Now I'm going to take that output and I'm going to put it into my function f of x. So I'm going to f the g of x, f of 4, and now I follow the rule for f of x, 4 plus 2, which is 6. Now what we're going to be doing with this is, instead of using numbers, we're going to go ahead and we're going to be using our functions. And so again, be very careful about the way things are written in terms of the order. Okay, so let's look at example number 1. And in example number 1, it says that f of x is defined as x plus 7, and g of x, x squared minus 4. So remember, f of x has a domain of all real numbers because it's a line. G of x has a domain of all real numbers because it is a parabola. So first what it's saying is f of g of x. So that means in f of x, which says x plus 7, every place that I see an x in that function, I'm going to replace it with g of x, which is x squared minus 4. So now I'm going to go ahead and I'm going to go simplify. So I have x squared minus 4 plus 7. So I have x squared, I'm going to combine negative 4 with positive 7, which gives me 3. The resulting function is also a parabola, so its domain is going to still be all real numbers. Now let's look at what we do it reverse. So if I have g of f of x, this means in g of x, every place there is an x, I'm going to replace it with f of x. So first what I do is I start off and I go ahead and I say, okay, x squared minus 4 from g of x. But I'm leaving a blank space where that x was. And now I'm going to fill that in with my f of x, x plus 7. And now I'm going to go ahead and simplify. So first I need to square x plus 7. Remember that means x plus 7 times x plus 7, which gives us x squared plus 14x plus 49. And now I simplify that. X squared plus 14x, 49 take away 4 would be 45. The resulting function is also quadratic, so the domain would be all real numbers. Okay, now let's go ahead and take a look at a second example. It says f of g of x. So here are my two functions. And we're going to go ahead and we're going to remember that f of g of x means in f of x, every place there's an x, we're going to replace it with g of x. So f of x is 3 take away x. So now I'm going to go ahead and replace the x in f of x with x over x plus 1. Now, f of x is a line, which means its domain has all real numbers. G of x, however, is a rational function. Remember, the denominator can't be 0. What would make it a 0? If x was negative 1. So the restriction on the domain for g of x is that x cannot be negative 1. So now we simplify. We haven't really gone over how to simplify these, so that's okay. At this point, if you're not sure how to do it, you could just leave it 3 minus x over x plus 1. Remember, the domain is the same as the restrictions on g of x, which is x cannot be negative 1, so we would write it as every number except negative 1. So it's negative infinity to negative 1, parentheses, because we're skipping over negative 1, in union with negative 1 to infinity. Okay, now let's go ahead and do the second one. So it's saying take g of x, which is x plus 1, and every place that there was an x, replace it with f of x. So the 3 minus x goes in there twice, replacing both x's. And now I go ahead and I simplify. 3 minus x can't be simplified other than 3 minus x. But over here, even though I have these parentheses, it's just adding and subtracting, so I combine the like terms, 3 and 1, which would give me 4 minus x. And that is as simple as you can make it. And now I'm going to worry about the domain. Remember, the domain means anything that would make the denominator 0 or give us an imaginary root. So what value of x would make 4 minus x 0? Well, that would happen if x was 4. So x cannot be 4. So our domain is going to be all real numbers except for 4. So we'd write it negative infinity to 4 in union with 4 to infinity.